Carbon dioxide, or CO₂, is a significant contributor to climate change and poses several environmental challenges. Human activities such as burning fossil fuels, coal, oil, and natural gas release large amounts of CO₂ into the atmosphere. CO₂ capture and removal are essential in combating climate change. Capturing CO₂ from industrial flue gases is an effective way to keep it from entering the atmosphere. CO₂ can be captured using solvents with two main methods for regenerating these capture materials: the well-established state-of-the-art thermal regeneration and the under-development electrified regeneration. While effective, thermal regeneration is energy-intensive and often relies on fossil fuels, which can offset some of its environmental benefits. On the other hand, electrified processes might be more energy efficient, especially when powered by renewable energy sources. However, for electrified technologies to truly compete with conventional thermal methods, a lot of research and development is still needed. Here is where DRIVE, Deep Removal of CO₂ and Innovative Electrification Concepts project comes in. The CETP DRIVE project's objective is to contribute to a carbon-neutral society by developing technologies and methods for applying cost-effective deep removal of CO₂ from industrial sources. The DRIVE project studies both the mature thermally and innovative electrochemically driven processes. To make sure these technologies work, can be upscaled, and to get more insight in their energy demand. In this video, we'll dive into cutting-edge electrochemical processes. So how do these innovative methods work? Let's find out. In these technologies, CO₂ is captured using an alkaline solution. This means that there are a lot of hydroxide ions present in solution, giving the solution a high pH. When CO₂ is bubbled through the solution, it can react with the hydroxide ions to form bicarbonate and carbonate ions. The CO₂ equilibrium in such a system is influenced by the pH, which determines the distribution of different carbon species: dissolved CO₂, carbonic acid, bicarbonate ions, and carbonate ions. At high pH around 10, the solution is rich in carbonate and bicarbonate ions. At low pH around 6, the solution is rich in bicarbonate ions and carbonic acid. pH lower than 6 increases the amount of carbonic acid, which is unstable, and CO₂ is released. Changing the pH can therefore change which chemical species there is in solution. So, how do these chemical reactions work in the CO₂ capture technology? In this technology, two major compartments are used: an absorption column and an electrochemical cell. The cycle is completed in 3 steps. 1. CO₂ absorption. Flue gas containing CO₂ enters the absorption column from the bottom. An alkaline solution, or high pH solution, typically with pH 12, is added from the top of the absorber column. The hydroxide ions in the solution spontaneously react with the CO₂ in the flue gas to form bicarbonate and carbonate ions. Ideally, all the CO₂ is captured and the CO₂ lean flue gas exits from the top of the absorber column. 2. CO₂ release. The solution is pumped from the absorber to the electrochemical cell into the analyte compartment. Simultaneously, hydrogen gas is fed via an adjacent gas compartment and crosses the anode, a gas diffusion electrode. The solution is acidified by oxidation of hydrogen gas to make protons and electrons. Consequently, the solution pH lowers to below pH 6. A solution is more acidic when there are more protons in the solution. Then the bicarbonate and carbonate ions are converted to carbonic acid, which then decomposes into CO₂ gas ready to be released. 3. Solvent regeneration. Next, the acidified and CO₂ lean solution is brought to the second compartment of the electrochemical cell, the catholyte. At the cathode electrode, a reduction reaction occurs. The electrons generated at the anodic compartment are now used in the cathodic compartment in the reduction of water to regenerate hydrogen gas for the acidification and hydroxide ions. The regenerated hydroxide solution can then be reused for CO₂ capture in the column, completing the cycle. Electrified regeneration of CO₂ capturing solutions, while promising, is still in the early stages of development and requires further research to improve efficiency and scalability. The CETP DRIVE projects contributes to a carbon-neutral society by demonstrating technologies for the removal of CO₂ from industrial sources at technological readiness level of 5 to 7. DRIVE will provide for the first time a holistic evaluation of deep removal technologies comprising technical, economic, and environmental analysis and validation in long-term tests at real industrial conditions. Continued research and development in these areas are vital to achieving sustainable and efficient CO₂ capture solutions. Stay tuned for the results.